Hi, today I want to talk about evaluating a joint training approach for learning cross-lingual embeddings with software information without parallel corpora on lower source languages. NLP tools require a huge amount of data to be trained. It is either in form of annotated data, for instance training language models, or they need a substantial amount of annotated data, for instance when we want to train a document classifier. This problem becomes more severe when we are dealing with lower source or morphologically rich languages. One way to address this problem is transfer learning. For instance, NLP transfer the knowledge captured in word embeddings when we train it in a rich source language and transfer this knowledge in a lower source language. Cross-lingual word embeddings provide us a way to do this transfer learning. Uh, they provide us a shared space that we can represent embeddings of two languages into the same space, and words that have similar meanings are going to be located closer to each other. Here you can see a 2D projection of the word embeddings in English and German. Uh, Using the current cross-lingual word embedding methods, uh, they they have a problem when we apply them on lower source and morphologically rich languages, and it is that since they are trained at the word level, they cannot provide a high quality embeddings for out of vocabulary words. One solution for this problem monolingual space is using software embeddings, but how about cross-lingual space? In this paper, we try to evaluate these four models and apply them on lower resource and morphologically rich languages and see which one is more capable to uh, provide higher quality embeddings for lower source languages. Duong et al., which is a joint training method, and that train word embeddings at the word level. Hakimi, Parizi, and Cook, which is an extension of Duong that incorporate software information during the training. Architects 2018, which is referred to as VecMap, which is a mapping-based method. Duval et al. 2018 is also is named Mimi, which is a post-processing model and applied on top of VecMap. Let's talk a bit in more details about Duong and Hakimi Parizi. Duong et al. In 2016 proposed a model that only requires two monolingual corpora as large as 5 million sentences. They combine these two corpora, shuffle the sentences, build a pseudo bilingual corpus, and use a bilingual dictionary and extended CBAL to learn cross-lingual word embeddings. They extended the CBAL function by adding an interpolation term. So during the training, not only they learn an embedding for WI, they also learn the embedding of its translation, WI bar, based on the same context. Hakimi, Parizi, and Cook 2020 extend their model following the similar steps as Bujanovsky 2017 FastSex paper by changing the scoring function and representing word embeddings based on the average of their subword embeddings. So not only they learn subword embeddings of WI based on this I have today is the context. They also learn the subword embeddings of WIR bar based on the same context. To compare these four models, we consider two intrinsic tasks, bilingual lexicon induction for in-vocabulary words and bilingual lexicon induction for out-of-vocabulary words. We consider these 12 lower resource and understudied languages for our experiments. For these two experiments, we consider for Duong and Hakimi, we consider the same config and settings that they reported in their paper. For Mimi and VecMap, we consider several settings, and here we report the best one. Source language is the lower source language, one of those 12 languages. Target language is English, and we can see the train and test section for each of these models. As you can see here, both Mimi and Hakimi 2020 outperformed Duong with a great margin. and Mimi and Hakimi Parizi show a comparable performance on this test. Here we can see incorporating software information during training had a significant impact on the quality of cross-lingual word embeddings comparing Duong and Hakimi 2020. For out-of-vocabulary bilingual lexicon induction, we followed the same step as Hakimi 2020. And so here we try to find the translation of an OOV word in the source language, which is translation in the target language is in vocabulary. Here you also see the different configuration for training. As you can see, WakeMap show a better performance for this task. As you can see here, Hakimi 2020 outperformed WakeMap with a great margin here, and it shows that incorporating software information during the training has a significant impact on the quality of OOV embeddings. Since Duong is a word-level model, it was not able to provide an embedding for out-of-vocabulary words, so we use a copy mechanism in this way that we assume the translation of an OOV is the same in the target language. In this work, we evaluated 4 approaches to learning cross-lingual word embeddings, and we considered 12 lower source and understudy languages. And Hakimi 2020 outperformed other methods, specifically on OOV test set with great margin. For future, I would like to consider the impact of morphological complexity on the performance of cross-lingual word embeddings. I would like to investigate other methods providing software information like BP, and I would like to consider these other downstream tasks, for instance, NER or pose tagging, focusing on lower source languages. Thank you for attending my presentation.